Hello everyone, this is Tianyu Wang. Today I will present a work on learning navigation costs from demonstration in partially observable environments. In computer games, the cost is usually given as scores between players. In more difficult tasks like robot navigation, designing a cost function is key to successful robot behavior. It is hard, if not infeasible, to design a cost function that incorporates all requirements like safety, efficiency, and dynamic feasibility. However, demonstrations of desirable behavior are significantly easier to obtain. This work takes a step forward by learning a cost function from demonstration in partially observable environments. The field of inverse reinforcement learning provides numerous tools to learn a cost function in a Markov decision process. Previous works learn a maximum entropy policy, such that the stationary state distribution matches that of expert demonstrations. The cost representation assumes a fully observable environment where features of the entire space are either given or learned. In addition, previous works rely on dynamic programming as the planning algorithm. It computes value functions over the entire state space, which is unnecessary in partially observable environments. We offer two contributions in this work. First, we consider a partially observable environment setting where the non-stationary cost function depends on previous observations only. Second, we propose a more efficient planning algorithm based on A star, which also provides closed-form gradients to optimize the cost function. Our problem is formulated as follows. We consider discrete robot states and controls, and deterministic transition function. An example trajectory is shown in blue dots on the right. At each state, the robot receives a noisy light observation in red. We're given expert demonstrations of state, controls, and lidar observations along trajectories from start to go. Our task is to learn a parameterized cost function such that its corresponding optimal policy matches expert demonstrations. We propose a model that decomposes mapping and planning. The learned cost function can generalize the control policy to new environments. More specifically, we decompose the cost representation into a map encoder and a cost encoder. The map encoder accumulates the occupancy log-odds ratio from noisy lidar observations at each step and predicts the occupancy probability of the environment. The cost encoder uses a neural network to predict the cost function from the occupancy probability. The cost function is differentiable with respect to the parameters of the map and cost encoders. Here we show the cost function for each control. Given this cost function, we can run a planning algorithm which returns the optimal cost to go values. The policy at the current state follows the Boltzmann distribution of the optimal cost to go for each control at the current state. To achieve this, we apply the A-star algorithm on a subset of promising states. This is more efficient than the dynamic programming methods that compute Bellman backups on the entire state space. To optimize the parameters of the cost function, we compare the predicted policy and the demonstrated control. The loss is backpropagated through the planning algorithm with a closed-form subgradient, which can be efficiently retrieved from the optimal cost to go values. Here we show the output of one example during training. The occupancy map probability in the middle, as well as the cost function for each control, converge after 40 epochs. Our model is capable of generalizing the learned cost function to new environments. Here we show a test trajectory that is not seen in the training set. The robot iteratively rolls out the next control by computing the policy at each state. For more details on the method and additional results, please visit our website. Also check out our new paper submitted to the Learning for Dynamics and Control conference, where we include semantic observations and more experiments in the Carla simulator. Thank you very much for listening. My name is Tianyu, and I'm happy to answer any questions over email.